Can you see my screen?
Yes, we can.
Oh, okay. Thank you very much. So last week we talked about one sample t-test. We talked about one sample t-test. We talked about paired t-test. So we are going to continue by talking about independent sample t-test. So what independent sample t-test does. So before we even start, let me even ask: is there any question before we start today's section properly, so we can address that before like moving forward? Is there any question? Okay, I'm going to take the silence for no questions. Mm. So what independent sample t-test does is that it compares two groups, like two groups of individuals. When we're talking about paired sample t-test, right? We have two groups, but the two groups is still the same group, like at different point in time. But this is like two entirely groups, like they don't have any correlation. So um maybe you have students in class A and students in class B. They don't have any correlation together. If you want to compare their math skill or their literacy skill ability, they don't. The students in class A and class B don't have relationship with each other. They are just two set of individuals that undergo a process. The process might be the same. Well, I don't know, and the process might not be the same. So it's just as if you are comparing patients on placebo and patient on actual treatment. So these two groups of individuals don't have any relationship together. So that's the difference between independent sample t-test and paired sample t-test. Paired sample t-test, they are the same group. They are the same group. You have two groups, but those in group A are still the one in group B. So it's just like maybe before and after, like before an intervention and after an intervention, comparing like what happened to a patient before an intervention and now after an intervention. It's still the patient. So we just move from a before phase to after phase. It's the person. But in this context, in this independent sample test, they don't have it's not the same patient. It's just like two entirely group, two total different groups. So now we have to start with examples. So a clinical trial randomly assigned 1,500 pregnant woman to daily iron supplements or placebo to assess whether iron supplement increase hemoglobin by the time of delivery. So only 982 women were identified as at the time of delivery. Other had a spontaneous abortion or did not return to the designated hospital for delivery. So we have the data, the iron trial. So what we want to do is that we want to compare the placebo group against the iron supplement group. So as you can see, the placebo group is totally different from the iron supplement group. So, so we have to like load our data, which is iron trial. So I believe everybody should have the data by now. So once you like try to like view the data, you are going to see the way the data is. So this is the way the data is. We have the hemoglobin concentration, and we have the treatment concentration too as well.
Please, could you increase the size of your screen, Daniel? I think the font is a bit too tiny.
Okay. Thank you. Sorry. So is this better?
I think so. Yeah, I think it's manageable.
Manageable. Let me try to increase it more. Yeah.
Yeah, this is nice. Yeah.
Okay.
Thank you.
So when you look at like the trying to like check what each variable entails, you see this is just like a numbering like SN number, like giving them its real number, and this is just the concentration. Why this gives the labeling, you probably know patients on placebo and patients on like what are you calling it, patients on placebo and patients on iron supplements. So I mean, let me scroll down. So okay, can you see? So it changes from like 1 to 0. So one group is on iron trial, one group is on placebo. So 0 to be placebo and 1 to be iron trial. So you want to compare the iron trial group against the placebo group. So that's what we want to actually do. These two groups are entirely different from each other. So that's like the difference between the difference most people make between paired t-test and independent sample t-test. In paired t-test, they are correlated, still the same individuals, but at another phase of another phase of concentration or another phase of method. But these, they are totally different from each other. So now going back to the question, so you know, might be very interested in viewing the first 3 observations. Might be very interested in like viewing the first 3 observations in the data set. So then using our table 1, you know, before you start, let me say, any statistical analysis, what you first learn to do is that you first learn to like do like a summary, how would I say, summary statistics, checking the median, the mean, and the standard deviation, and number of samples, sort of. So that gives you like a very quick information about the data you are working about. So you are working on. So now we want to like summarize our data using the create table 1 package that we have. We've been learning for some weeks, like I think 2 weeks back now. So you have to like specify the variable you want to summarize, which is the HB. After specifying the variables, you create table 1, variables take vars, and you struct like you structure, like it needs a structure because we have 2 groups. We have the iron supplement groups, and we have the placebo groups so as well. So once you click on this, so yep. So we are going to have these two, we are going to have these 2 groups. So the first one now is the treatment option is 0, which is placebo. So how many patients do we have? We have 501. We have 0 missing. We have percent of missings to be 0. We have the mean HB. We have the standard deviation. We have the median. So we have the 25 percentile. We have the 75 percentile. We have the minimum. We have the maximum, and the skewnesses and kurtosis. So now for like the for women on iron supplements, now we have 481. So we have 0% missing, 0% percent missing. We have mean to be 12. We have standard deviation. We have median. We have percentile, 25 percentile. We have 75 percentile. We have minimum. We have maximum. We have skewnesses and kurtosis coefficient too as well. So before, like, what we need to know is that we need to, okay, before then you have to like do like a kind of visual plot. So for this kind of data, which kind of visualization do you think will be suitable, like, to explain this kind of data, which is box plot? Yeah, box plots actually do justice to a whole lot of stuff like this. So, you know, once you use the function called box plot, HB, that approximation sign, treatment. So once you do that and you specify your data that you are using, the data you are using, you use the x-axis and the y-axis. You give the label to the x-axis and the y-axis. So let me just run this line of command so you see what this does. So we have to box plot already. So this is for women on pregnancy women on placebo, right? And this is women on what are they calling it, on iron supplement. So from this visual itself, you can see that without even from this visual, you can see like you can see the changes. If there is like changes on between their hemoglobin concentration between the two groups, you can see like if there is like slight changes. But what you want to actually ask is that, does this changes, is it significant? Because sometimes there might be element of change, but the change might not be really significant. You can't tell me that the difference between my weight and someone's weight is like the difference is like 0.00001 kg, and is that really significant? Those are the questions we really want to answer. So now we come to our formulation of hypothesis, since we have two groups. So the null hypothesis is always saying that the hemoglobin concentration, there is no significant difference between the hemoglobin concentration of women who are on placebo against women who are on iron trial. So why the alternative say there is significant difference between the two groups? There is significant difference between the two groups, actually. That's what that is going to say. So we are still going to use like our t.test, actually, because that's like the standard formula for like comparing two groups, t.test. So when you say t.test, you specify the variable of interest against the group. Like why you use that approximation sign against the group, then it's going to ask you data, because we are trying to like do a two-tailed test. So that tells us if there is significant difference. It does not tell us if one group, we are not trying to like know now if one group is actually greater than the other one. We are not interested in that. We just want to know if there's significant difference between the hemoglobin concentration. So if you run this now, we are going to have which two tests, I think they call it which man two test, two sample test, like that kind of. So they are going to have the test value. This is the test value. It's negative 7.0005. This is the degree of freedom. So we have the p-values that actually tells us that actually gives us the information we are looking for, actually. So can someone please just unmute and interpret this p-value for us? Anybody?
Yes.
Okay.
It shows a strong statistical significance between the two groups. Very strong.
So are you okay? You are saying that there is statistical significance between the two groups, right?
Yes, sir.
Oh, okay. Thank you very much. So that's what we are trying to do. So now are we rejecting the null hypothesis, or we fail to reject? That's another question I'm going to ask again.
We are rejecting the null hypothesis.
So if I may properly ask, why are we rejecting?
Because we have shown that there's a significant difference between the two groups.
Okay, we have shown. How do we show that there is significant difference between the two groups?
By doing our t-test and seeing our p-value, and also looking at the confidence, 95% confidence intervals.
Okay. Oh, okay. Yeah, I totally like get what everybody's saying. But there is something I want you to note. There is always a threshold for rejection. So whenever you are trying to like make decision regarding the null hypothesis, or regarding maybe statistical, you have to like compare your p-value to a benchmark. Like,
so you mean the p-value is less than 0.05? Is that what you want to say? Okay.
Exactly. Yeah. Exactly. So in many contexts, maybe if the p-value changes, if the level of significance changes now, the way like if you compare it with 0.05, it might not be significant, but when you compare it against the 0.01, it might be significant. So that's why you need to like make reference to like the level of significance you are comparing your p-value to. So for that, so now we have like 95% interval, confidence interval that shows us like the range of number which the actual difference between the actual difference like falls. So the actual difference between the mean, like between the mean like between the mean of the group on placebo and the mean of group of people on IO supplement, like the difference between the mean. This confidence interval tells you the actual like range in which the difference between the two groups mean falls. So which is this? So it's going to give you the sample estimates too of the mean of people on placebo and of the mean of people on IO supplement. So we've already make our conclusion. So that's actually what t-test two sample t-test does. But you know, when you are trying to do it like is it bi-directional test, maybe checking which group is actually greater, what you just have to do is just to like add another set of command here. Maybe we want to test okay, now we know that there is significant difference between the group. We are interested in checking like, oh, is placebo group, is it greater than is hemoglobin group is iron group greater than placebo group? We might be interested in knowing that. So you can just come and specify your alternative, right? Incoming alternative equals I hope it takes that. Yeah, so it takes that. So now, if you want to check now, you see that from the p-value, if you compare the p-value against the benchmark, like a threshold of 0.05, you notice that we fail to reject the null hypothesis, and we fail to reject the null hypothesis and conclude that the placebo group is strictly not greater than the iron supplement group. So if you are trying to like do like a unidirectional test, we in the two-sided test, we notice that there is significant difference. But we are trying to actually choose which one is greater than which one, because two-side tests will not tell you, two-tailed tests will not tell you which one is greater than which one. If you do this test like other like in the other side, you are going to notice that the iron supplement group is actually greater than the placebo group. So that's what this unidirectional test tells us. It tells us the direction, which group is actually greater than another. So now, so any question? Okay, I'm going to take that for no. So now we'll be talking about ANOVA. So what you need to know is that the difference between ANOVA and independent sample t-test is that ANOVA involves 3 or more groups, while independent sample t-test involve like comparing means between 2 groups. Yeah, that's what independent sample t-test does, 2 groups, while ANOVA involve like comparing means between 3 or more groups. Yeah, I know there is before, okay, don't let me say before ANOVA, like there is a way you can use independent sample t-test to compare 3 or more groups, but it's very stressful because you start taking group A, compare with group B, group A with group C, group B with group, no, which in like statistically is like it doesn't really make sense, because when you have like multiple groups, like let me say a very huge groups, you cannot start doing that. That was the idea behind ANOVA. So ANOVA is full meaning of ANOVA is analysis of variance. So we are trying to like check the compare the means across 3 or more groups. So and ANOVA is very, very sensitive because it has some assumptions. If it violates those assumptions, then ANOVA, you cannot use ANOVA even if you have 3 or more groups. if like our data violates the assumptions. Which one of the assumption is the data must be normally distributed, or the sample size is large enough. So, and when they say sample size is large enough, they try to like put the benchmark at 30. If it's greater than 30, that's when the central limit theorem comes to place in. So if it's extremely large enough, it's greater than 30. Even if it does not, if it's not normally distributed, it's assuming that it's assumed that the sampling distribution of that means will be normally distributed. So the standard deviation must be approximately like equals to each other. The standard deviation of group 1, group 2, group 3 must be kind of similar. Not really, even if there is any difference, but must be approximately like equals. So, and the samples are drawn independently. That is, those in group A will be totally different from those in group B. It's totally different from those in group C. It's not like having the same people, the same person in group A, group B. No, you cannot. So across all treatments, they are totally different. So let's try to like work on one example. So
I'm sorry, I have a quick question. I raised my hand. Can you make the point again about the sample size being 30 or more and what that means? I missed it.
Okay. All these tests we are working with is parametric tests, so they are like distributional tests. If your data is not like normally distributed, when you have like a how would I say, when you have like when you have this histogram, right? Is histogram? Yeah. When you have histogram and you see that the shape of the histogram is like it's tilting to the right, extreme right or extreme left, so that is not a normally distributed data. So if you have like a normally if you have a normally distributed data, you will notice that the mean, the median, and the mode will be approximately equal to each other. Yeah, we've talked about that in previous classes. But in all these tests, for this test to like hold, for ANOVA to hold, for one sample test to hold, for independent sample test and pair sample test to hold, your data must be normally distributed.
I understand that, but you said something about the sample size being greater than 30. That's what I'm asking about.
If your data is not normally distributed now and you have a greater sample size, so most ideally, like they said when the sample size is large enough, but the the benchmark for that large enough is greater than 30. Once it's greater than 30, your sample size like is greater than 30, then you can assume that the data is normally distributed. Because if you have like sample size greater than 30, it is assumed that it's not that it's assumed. Like once you like try to like collate the sampling distribution of the means, or like you have to sample, take the means, sample the distribution of the means, you are going to see that as the sample size increases, the sampling distribution of the means tends to be normal distribution. That was the assumption behind sample size greater than 30. It's large enough. When they say it's large enough, but that cutoff for large enough is 30. Some says 50, but 30. So
thank you.
Yeah, so that's so now let's take our example for the ANOVA. So you conduct a 3-arm clinical trial to assess the effects of new drug X on systolic blood pressure among adults in Freetown, and compare this systolic blood pressure after 12 weeks of using this the drug. New drug X is compared to active comparator, old Y, and to placebo, right? So we have like 3 groups. We have new groups actually. So we have new drug X.
Good afternoon. So sorry to interrupt you. Please, I don't know if the files we're currently using for this class could be sent, because I tried downloading it from the classroom, but I'm getting an error message, and I think some other people also don't have the files, and I put messages in the chat. I don't know if there's an R Lab board, but it's not also on the classroom. I don't know where other people who are working on it have gotten it from, but if those files can be sent here, so please, thank you.
Okay. But I think you can find that. Okay, since you said you cannot download it from the classroom, coming. Let me try to find the link and share the link over here. Mm-hmm. Okay. Oh, okay, okay. You can find the R Lab 3. The link has been dropped, so you can check the that link. You are going to. So you'll be able to download the R Lab 3 from the link. So
Okay,
Okay.
thank you so much. Does it have the CSV file? Because it's just the RMV file for the lab. Like the CSV files, for example, with iron trial and the BP trial, the files are not like I'm getting an error message when I try to download it from the classroom. So I don't know if other people have downloaded it and if they don't mind sending it here.
okay, you don't have the like. Do you have the the data, like the data we're working with, like the ion trial data and the BP trial?
No, I don't have those files.
Okay, I think you can keep checking the chat box. So the link to the data has been updated here in the chat box. But just in case of next time, once you just go to like the Google Classroom, I think it's at the extreme end of the like the bottom that you're going to see the data and the file for the class. So yeah. So Oladimeji, please, we can hear you.
Yeah, I think I've gone to the classroom and I have the links. The issue that I am having, which is probably similar to what others are saying, is when I click on that link, I need to log in. And when I do that, it tells me that the file is not available. So that's like the issue. It's not really not just the link, it's that when we click the link, we are not able to get the file.
Oh, okay. Um, let me see if I can find a solution to that. Actually, data's still not available.
I don't know if anybody already has the file, and if you can just send it directly in the chat instead of in the. I don't know if that's possible.
Oh, okay. I see. I see. I see what you're saying. Uh, hmm.
Hi Daniel. So I would escalate now and I'll drop a chat in the box.
Oh, okay. Okay. Thank you very much. So, can you please just pause the recording for us so we try to like solve this problem and get everybody on track before we continue?